All right, hello, folks. This is going to be the second, let's see, the second video of this week. I'm going to balance equations. This is something we need to make sure we have a handle on, so we're going to do a little bit of these for the next week or so. So what we mean, we're going to balance chemical equations. And when we have a reaction, and we saw from the last video, you got the reagents and you got the products, the number of atoms on the left-hand side of that equation must equal the numbers on the right. And this is why we said this, is because years ago when we first started actually going from alchemy to chemistry, people were wondering how things could be magically appeared or they can disappear when we add two things together. And we were wondering about this, and then scientists realized that, hey, we're making a gas. We're blowing up a balloon or something, something's occurring. And we have to include that in our equation. And then everything kind of fell into place saying, hey, matter is not created nor destroyed, but it's just transformed in some way. Transformed from a liquid to a solid. Two liquids come together in a double displacement reaction to get a solid. We single displacement add acid, a liquid to a solid metal, and we end up producing hydrogen gas, that type of thing. So no matter what we have to balance the equations. And there's a couple rules we need to know. Here's the method of writing the chemical reaction, balancing chemical equations. And first, you're going to write the reaction. 95% of the time, I'm going to give that to you. And then we're going to count the atoms on each side of the arrow. I'm going to list them down, go how many carbons, how many oxygens, whatever. And then we're going to start balancing. First thing we need to do is figure out which one's the heaviest element. And sometimes you might have two or three heavy elements, you just got to pick one. I usually like to find the heaviest, and that may be the easiest. Or it may change as we do the balancing. Don't worry about that. You always go back and balance it back later. Now, one thing we're going to do is we're going to always add. We don't subtract. We never subtract from these chemicals. If you have something, we always got it. It's always going to be there. So don't subtract, always add. And we're going to add molecules and units by changing the coefficient. And that means that in some of these, if we have two different elements bound together in a molecule, you can be adding, you want, say, carbon, and we have carbon dioxide. So we want to add carbon. We're also going to be adding more oxygen in terms of carbon dioxide. That's going to happen. This is why we do this method. It will take account of that. It's going to be you're going to be doing a lot of counting numbers. Nothing too strenuous, but you're going to be doing some counting. Now, hydrogen and oxygen are last, just because they're the most prevalent elements in most of these reactions. And if we have H2 or O2 are present, we're going to use that last. Now, B is the hard one. This is where it gets kind of complicated. There's an odd number of atoms needed, and we're talking about hydrogen and oxygen. We're going to need half that molecule to balance the elements. So if we need 5 oxygens, 5 oxygens. And remember, O2 is O double bond O. To get 5 of them, we need 1. There we got 4. Now we just need a single. So we usually write it as 5 halves. So we got 5 halves O2. And for every O2, we got 2 O's. And those cancel, and we have 5. That's one way to look at this. And we'll show you what to do with this a little later on in one of the examples. We've got 3. Because nature hates fractions. We want to get rid of that. So let's look at the simple problem first. This is a way to get rid of rust. You have iron, and you stream hydrogen over it in terms of heat, and we end up with iron and water. And the thing is that this kind of works if you got a big block of metal, but sometimes iron rust can actually, if it's deep inside the iron piece of metal, it can actually weaken it. So, actually this is kind of dangerous too, because a little bit of oxygen and it goes boom. So this is how this is going to react. So we're going to count. So we're going to count the elements, Fe, O, and H. We got 2 on the left, 3 oxygens and 2 hydrogens. And on the right, we have 1 iron, we have 1 oxygen, and we got 2 hydrogens. Remember, this goes with the hydrogen, not the oxygen. So everybody's going, oh, look, hydrogen's balanced. Well, let's see what happens. All right, let's balance iron first. That's the heaviest. We got 2 on the left. We need 2 on the right. So now this is where my language kind of gets confusing. And students will say, well, we need 1. Well, they really meant we need and then 1 added or 1 additional for a total of 2. To do that, we put a 2 in front of the iron. 1 plus 1 is 2. If there's nothing in front, if we have no coefficient, we assume, and it's safe to assume that we have 1. So now let's go to the oxygens. We got 3 on the left, we got 1 on the right, and we need 3. 3 oxygens and 3 oxygens. That turns to 3, and oops, 2 times 3 is 6. That changes to 6. So that when you put a coefficient in front, we're changing everything, and this is okay to do that. Now we come to the left-hand side because we've got 6 hydrogens on the right, we've got 2 on the left, and we need 3 units of H2 to make that 6. Let's see, 2 and 2, 3 and 3, 6 and 6, everything's balanced. So we rewrite this as Fe2O3 plus 3H2 yields 2Fe plus 3H2O. Everything is balanced, everything's happy, and this is how you solve these things. You go back and forth to make sure everything's balanced. And sometimes you may have it balanced initially, and then it may change when we balance everything else, and that happens. So let's look at this one. Here's another reaction, another example, and this is where this is higher level, and I did this a couple years ago, and I'm changing it, but I'm going to include this example in here. We got butane plus oxygen gas gives CO2, and this is a combustion reaction. Now I'm including this because this can be a little bit hard, is it? So you add heat or flame, and this burns. This is your Bic lighters, and if it does it completely, we're gonna get carbon dioxide and water. And see, I've done part of this, and this is carbon, this is hydrogen, and this is oxygen. Now, so we got 4. The heaviest one is carbon. And we'll do oxygen last because we have this O2 here. Now you notice we have the state of each element, each compound. They're all gases. And this is important for combustion, is that anytime you have a combustion reaction, we're looking at gases. Liquid butane does not light because there's not enough surface area for oxygen to react with the butane. That occurs on the surface or as a gas. So this is the reaction we're looking at. So we need to have 4 carbons. Since we have 4 on the left, we need 4 on the right, so we change this to 4. And we need 4 units of CO2 to make this happen. Or if you want to say 3 additional units to come up with a total of 4. Now, 2 times 4 is 8. We got 8 more oxygen. We got a total of 8 oxygens, but plus 1, that's 9. So we got to change that to 9. Remember, every time you add a coefficient, you got to change all the elements involved in that substance. Now, next is hydrogen. Remember, oxygen's last. So we got 10 over here. We have 2 on the right. And to get to 10 hydrogens, we need total of 5 units of H2O. So I'm going to put a 5 here. 2 times 5 is 10. Beautiful. Now we've got to add the oxygens again. 2 times 4 is 8 plus 5. That should give me 13. Now we come over here. We have 13 oxygens on the right, 2 on the left. And that is because we have the molecule O2. Now this is where I like to do fractions, and this is the way I like to do things. There are a couple other ways to solve this, to mitigate this, and if you do it that way and you get the right answer, those are fine. But I'm going to show you this way. we need 13. But since we have since oxygen has a molecule of 2 atoms each, I'm going to go 13 over 2. That is balanced. Now we have 13. We got 13. But ladies and gentlemen, nature hates fractions. We cannot give half a molecule of O2. It doesn't work. So to get rid of the fraction, I'm going to multiply the whole reaction by 2. So I'm going to 2 times everything. And I'm going to do this on the bottom. So we've got 2 C4H10. So I'm multiplying the coefficients by 2. That's 13O2. Yields 2 times 4 is 8 CO2 plus 10 H2O. And now if you do all the counting, it's balanced, and this is the correct answer. If you give me this, I'll subtract 1 point off your score. Nature, I don't want a fraction. I want you to multiply that denominator through to get this. And this is what this is saying. All right. And I'm just going to go through here. Let's go to this one. And now we have an equation where we got chlorine on both sides. Last example. CS2, carbon disulfide, plus chlorine gives me carbon tetrachloride plus disulfur dichlorine. And that's a mouthful. CSCl. 1 carbon on the left, 2 sulfurs, 2 chlorines. And on the right, we got 1 carbon. We have 2 sulfurs and 4, 5, we got 6 chlorines. This is easy. All right, carbon's balanced, sulfur's balanced, chlorines are not. We got 6 on the right, 4 from here, 2 from here. So we need to change the coefficient for a Cl2 to get to 6, and that will give me 3. I need 3 units of Cl2 to give me 6 chlorines. And then my answer is CS2 plus 3 Cl2 yields CCl4 plus S2Cl2. And now on the test, I'm going to count E. You're going to gain a point for each coefficient. If you leave it blank, I'm going to assume 1, which is fine. Don't put a 0 there, folks. I'll count that wrong. And there we go. That is the answer. If you have any questions, please let me know. And you can do this on your own.